Alright, so this video is about continuity. The first thing is the definition of continuity. So this is the formal definition of continuity. A function f is continuous at a number a if the limit of the function as x approaches a equals to f of a. Alright, so notice that the definition implicitly requires three things if f is continuous at a. One, f of a is defined. Alright, so what we mean by defined means that a is in the domain of f. So a isn't a number that is undefined or causes a vertical asymptote or hole in the graph that doesn't exist elsewhere. Is actually defined, actually has a place on the graph, someplace that a actually exists. Two, the limit of f of x as x approaches a actually exists, meaning the left-hand limit and the right-hand limit actually merge towards the same number. So the limit actually does exist. And three, the limit of f of x as x approaches a is equal to f of a. Alright, so that means that if we had some function, when we approached it, let's say it looked like this, and this is f. When we approach whatever that number is, a, from the left and right, they both merge toward the same number, and that output here is the same thing, like it's not a hole there and the graph exists someplace above it, below it, or elsewhere. It actually occurs where you would think it should occur. So I'll pause the video if I were you. I'll copy down anything that I'll copy all these things down, and I'm about to erase this screen and start talking about some other stuff. So I'll pause it and copy it. Because this is the first example. The question says the graph here shows the graph of a function f of x on the interval from 0 to 4, where it exists at 0 and exists at 4. So basically from here to here is the only section of the graph it shows. At which values of x is the function discontinuous on that interval? So you will have to consider outside of 0 or outside of 4. Just looking on this interval. So I think you probably can answer without me. Pause the video and you tell me, or you write down what you think the places this function is discontinuous at. So pause the video and give it a shot. Okay, so you probably said, well, it's discontinuous at x equals 1. Alright, so the y, you could say it's discontinuous at x equals 1 for 1 because the limit doesn't exist there. And that's one of the things that must happen. The limit must exist at 1, and it doesn't exist at 1. And then it's also discontinuous at 2, right? Because 2, you have this hole in your graph, and the function exists elsewhere. And the reason why it doesn't exist at 2 is because f of 2 does not equal to the limit as x approaches 2 of the function f of x. So since that's not equal, that was one of the rules that was stated in the definition had to be true. So since this dot's out of place, not where the hole is, f of 2, the output of f of 2 isn't the same thing as the limit of f of x near 2. So anyway, so that's the reason why. Those are two places that this function is discontinuous. And those are the only two places this function is discontinuous on the interval 0 to 4. Alright, I think you got that. We'll go to the next note. Alright, so in the last example, I gave you a graph right away. And we figure out where it's discontinuous. This time, I'm giving you equations. You're going to figure out where those equations are discontinuous. And I always would kind of start with the graph. It's always a good place to start so I can have a good understanding of what the function is going to be doing. But anyway, it says, where are each of the following functions discontinuous? Let's start with the very first one here. Alright, so it's blocked off. Looking at this function, you should know that this function either has a vertical asymptote at x equals 2, or it may have a hole in the graph at x equals 2. The only way to know whether or not that's a vertical asymptote or a hole is you would try to factor the numerator, of course, to see if anything factors out, and then that would give you a hole. So if that's true, the numerator factors to be x subtract 2 times x plus 1 divided by x subtract 2. So because we have factors in common, x subtract 2 and x subtract 2, they would cancel each other, leaving you with just x plus 1 as this function. So if you graph it, this function would essentially look like x plus 1. So if you graph it, it would look like the function that has a slope of 1 and a y-intercept of 1. So this is probably enough to graph it with. And if I actually graph it, let's make the graph yellow. If I actually graph it, I know my y-intercept is 1. I know my slope is 1, so I'm going to rise 1, run 1, rise 1, run 1. And the graph looks something like this. Now, we know that at 2, there's a hole at x equals 2. Why is it a hole? Because in the very beginning, 2 was undefined. Like 2 is not a part of the domain. So 2 doesn't exist for this graph because it would make it 0 in the denominator. So I know there, it should be a hole in the graph. So this is where that's 1, and this is 2. So right here should be a hole in the graph. I'll make it yellow. Circle around it. So I know there's a hole there in this graph. So it says, where is this graph discontinuous? Well, taking a look at the graph, it's pretty easy to tell that this graph is discontinuous at x equals 2. So it's discontinuous. It's discontinuous at x equals 2 because f of 2 is not defined, right? There's one of the rules by definition of continuity had to be true. F of 2 had to be a part of the domain. Since x equals 2 is not a part of the domain, it couldn't be continuous. It has to be a closed dot there too. All right, so that was the first one. Let's look at the second one. Oh, you need that as a note. I'll copy it because I'm about to erase a lot of this stuff. All right, so going to the second example too. The function is piecewise. It's defined on different intervals. So it says f of x is a function 1 over x squared if x is not equal to 2. So all the numbers other than 2, it looks like this. And it's f of x is equal to 1 if x is 2. So you have to have a good understanding of this graph. You can graph and calculate if you don't know what that graph looks like. You can graph y equals this. You might just know that that's a hyperbolic function that should look something like this. Let's make it blue. It should have a vertical asymptote at 0, because x can't be 0. But on the left and right side, the function should kind of curve up towards asymptote. It should asymptote towards 0. So it should asymptote towards 0 this way. It asymptotes toward x equals 0 that way, and y equals 0. So you have two asymptotes in this function. So this is what that function looks like. And it's true everywhere except when x is 2. So I'm going to have to go over here, consider where x is 2, and at that place, it doesn't exist there, as it should. So x equals 2, there's a hole right there above the 2. But then the second part says, when y equals to 1, x equals to 2. So when x is 2, the output is actually 1. So let's say 1 is like here. Not really sure what it really be, so I didn't really make the graph to scale. But let's say it's actually here. So if that's the case, when x is 2, the output is actually 1, which would be there. Now, again, I didn't make the scale, so it might be below if you actually graph it on your own. I just kind of gave a visual understanding where that graph is. But so it exists someplace else off of where the rest of the curve exists at. So that's what the graph looks like. So the question is, where is the function discontinuous? And, well, where is it discontinuous? You know, if you look at it, what would you say? You'd probably say it's discontinuous at, well, all right, so I'm going to put it out using a sentence. F of x is discontinuous at x equals 2 because, so why would it be discontinuous at x equals 2? Because in this case, f of 2 does exist. It's 1. Because the output, when you go to 2, output is there at 1. The y value is 1. So it does exist. So it's unlike the last one where it didn't exist there. That's not the case here. But the reason why this isn't continuous is because the limit as x approaches 2 of f of x isn't the same thing as f of 2. So you take a look at it, the limit is whatever this number is approaching. All right, whatever these two sides are approaching, whatever that is there, whatever that is, that's what the limit is. But f of 2 is clearly 1. So that's the reason why this one is discontinuous by definition. Okay, let's move on to another example. Oh, but if any of that is new, you should copy it and then pause the video and copy it and then join us. All right, so going on. All right, so this is a theorem. The following types of functions are continuous at every number in their domain. So one of the functions is so polynomials. You know, functions look like x squared, x cubed, x to the 5th, and there's no variables on the bottom of the fractions, or x to the 1st for that matter. Any polynomial function. Another one is root functions. So if you think about square root of x, cube root of x, etc., all those are root functions, and they're continuous at every element, every number within their domain. Makes it a bit different from polynomials, because polynomials are different for are continuous for all real numbers. Like there's no number you can't plug into a polynomial. So you can plug in any number you want, and you're not going to get asymptote. You're not going to get Holograph if it's just a basic polynomial. With roots, though, you'll have numbers that can't exist at, but it distinctly says in their domain. So as long as it's in their domain, it's continuous everywhere else. Rational functions. So functions with variables on the bottom, 1 over x, x squared plus 1 over 2x, etc. Any function with a variable in its denominator is continuous at all the numbers in their domain. Again, there are clearly numbers x can't be in both of these functions, and it's not going to be continuous at, but every other point in its domain is going to be continuous forever. All right, and the last one is, so trig functions. So trig functions at all the elements in their domain, sine, cosine, tangent, they're going to be smooth, not any breaks in them. There will be sine or cosine. Tangent isn't really smooth because it has breaks in it. Again, those breaks don't exist in the domain. It's already defined, not being a part of its domain. So it still is true that it's continuous at every point that is within its domain. All right. So anyway, those are the 4 function types that are continuous at every number in their domain. All right, so I'll pause that and get any of that as a note. And I'm about to erase the screen and give you one final note. All right, I'm considering about 3 or 4 of these functions, but this is the question: on what interval is each function continuous? This first function is polynomial. Why? Because there's no variables in the denominator, and it doesn't have any square roots around it, or irrational exponents or negative exponents on the variables. Because of that, I know it's a polynomial. So for that matter, polynomials are continuous everywhere. All real numbers of x. So this this interval that's continuous from negative infinity to infinity. I can just write it that way. It's continuous there. This one isn't a polynomial. It's definitely a rational expression, and its 2 numbers make this 0. X cannot be 3 or negative 3. So because of that, this function is continuous from negative infinity up to the number 3, or better yet, negative 3. That's the first number on the left. And there's a closed circle there, open, soft bracket there. And then from negative 3 to 3, soft brackets. Just for the record, you could have tried to factor this numerator to see if any factors canceled out with the denominator. But even if they did cancel out, it would create holes. So no matter what, it would still be a point of discontinuity. So it's continuous everywhere else, because these numbers aren't a part of the domain. So anyway, that's all I have. Good luck.